In this section, we're still talking about vectors, but we're going to move away from vectors that have scalar components to now vectors that have function components. And these are called vector-valued functions, and they form curves in space. So typically, we would write a vector-valued function as r of t, and instead of having components r1, r2, r3, this vector is going to have functions as its x, y, and z components. And these functions are all going to be functions of t, which makes our overall vector-valued function also a function of t. So it's just a vector that has functions as components. The most basic type of vector-valued function is a line in space. So in order to write the equation for a line in algebra class, we had to have the slope and a point on the line. Well, slope in three-dimensional space would be equivalent to having a direction vector. The components for a direction vector describe how our coordinates are changing in the x, y, and z directions. So we would have this direction vector we call v. And we would know the components for v. Let's say they're a, b, c. We would also need to know a point on this line, and we'll call that p. And it has coordinates x1, y1, z1. So what's unique about a line in space is that if we pick any other random point on this line, which we'll call Q, the vector that we create between P and Q should be parallel to vector V. And we don't know what Q is. We're trying to come up with a generic representation for every point on this line, so we're just going to use variables x, y, z to represent point Q. So PQ is parallel to V. And what that means is that the components for PQ and V are scalar multiples of one another. So if we create vector PQ, we're going to do the Q coordinates minus the P coordinates. You always do terminal minus initial. We're going to have x minus x1, y minus y1, and z minus z1. So these components should be scalar multiples of a, b, c. And for our scalar multiple, we're going to use the variable t. So we're going to say a times t, that's the x component for v, should be x minus x1. So a is a scalar multiple of x minus x1. And we need to use the scalar multiple for every single component pair that we do. Back when we checked for parallel vectors a few sections ago, we said if any of those ratios came out different, then it wasn't parallel. So we need to make sure that we're using the same ratio of t every time. So bt is equal to y minus y1, and ct is equal to z minus z1. So if we were to solve these equations for x, y, and z, we would get a vector-valued function, r of t, which has components a times t plus x1, b times t plus y1, and c times t plus z1. So this is a vector notation for a line in space. We could also write them as a pair of a set of parametric equations. And that's just when we pull each of those out and identify them individually. So we would have x of t equals at plus x sub 1, y of t equals b times t plus y of 1, and z of t equals c times t plus z sub 1. So you see it's the exact same thing we have here. We're just identifying them individually when we write them as parametric equations. There's a third but less common form that we can write the equation for a line in space, and that's with symmetric equations. If you take those three equations that we set up based on the fact that we had those two parallel vectors, we had a times t equals x minus x sub 1, b times t equals y minus y sub 1, and c times t equals z minus z sub 1. All of these t values are the same t values. So if we were to solve all three of these equations for t, technically all three of the expressions that we would get back would all be equal to t and thus equal to each other. So if we did that, if we solved each of these for t, the first one, all we have to do is divide over those coefficients. So we'd have x minus x sub 1 over a equals y minus y sub 1 over b equals z minus z sub 1 over c. So this format right here is called symmetric equations. There are two equal signs, and symmetric indicates that they are all equal to the same value t. Now let's take a look at a few examples. The vector valued function for the line that passes through the point, and we're going to call this our P, 2, negative 1, 4, in the direction of V, which has components, (3, negative 2, negative 1). So we don't have to every single time work this out by doing creating a PQ and then setting up a ratio with V. We could just jump straight to the formula. But just to help you get a handle on that formula, I'm still going to work it out with the ratios. So we just pick a generic point Q, which we're going to force it to be on the line. We're going to create vector PQ. So I'm going to have x minus 2, y plus 1, z minus 4. And PQ, since P and Q are both on the line, PQ must be on the line. We know V is also pointing in the same direction as the line, which means these two vectors must be parallel. So they must be, all those components, when we set them up as a ratio, must have the same ratio value, which we're going to call t. So 3 times t must equal x minus 2. Negative 2 times t has to equal y plus 1. And then negative 1 times t has to equal z minus 4. And if we solve this for x, y, z, we will have the components for a vector valued function, which is 3t plus 2, because we're solving for x, negative 2t minus 1, and negative t plus 4. The 3, negative 2, and negative 1 came from our direction vector, and then we got the minus 2 plus 1 minus 4 because we created a vector between P and Q. And when we do that, we do the Q components minus the P components. And we're using 2 as our common ratio. Let's try another one. This one's a little bit different. we are going to find parametric equations for the line that passes through the points. Five, 0, -1, and 2, 3, 0. So we're given different information this time, but it's still enough information to figure out the parametric equations for the line. The two most basic pieces of information that we need are a point on the line, and we've got 2 of them, so we're all set with that. And then we also need a direction vector, a vector that points in the exact same direction as our line. But since we have 2 points on the line, we can create a vector between those 2 points and use it as our direction vector. So we can call this, I'm just going to call it R and S. And our direction vector, I'm going to make by calculating vector RS. So we're going to do the S components minus the R components. 2 minus 5 is -3. 3 minus 0 is 3. And 0 minus -1 is +1. If both of those points are on the line, then the vector that we create using them will point in the same direction as our line, and we can use it as our direction vector. And then now we could use either one of those points, R or S, to set up our parametric equations. And I'm not going to go through the whole common ratio with t here. I'm going to jump straight to the answer, because the pattern that we see in the setup of these equations is exactly the same every time. We always have these coefficients come from the components of our direction vector, and then these constants come from the point that we're using on the line. So as parametric equations, we would have x of t equals -3t, and then you have to decide whether you're going to use R or S. So we could either say +5 or +2, but you have to pick one and be consistent and use that same point every time. So I've used 5, which means I'm using R, so all of the rest of them have to use R as well. So y of t is going to be +3t plus 0, and then z of t is just 1t minus 1. Now we also could have used point S, and our answer would look completely different, but it would still be the same line. So that's one important thing to point out here, is that the equation for a line in space is not unique. It's possible to come up with many, many different representations that, once graphed, all make the same exact line. Part of what dictates the fact that these 3 parametric equations are going to create a line in space is the fact that they are all linear equations. They all have t to the power of 1. One more example, and this one is going to involve the symmetric format that we talked about earlier. Let's find vector format for the line in space that passes through the point -2, 7, 3, and that is parallel to the line x over 5 equals y plus 1 over 2 equals z minus 8 over negative 3. So remember what we need in order to write the equation for our line. We need a point that's on the line. Well, they did give us that. We also need a direction vector, which is a direction. It's a vector that points in the same direction as the line. And that wasn't exactly given to us, but what we were given is a parallel line. So remember back to what you know about parallel lines from algebra class. You may remember that parallel means same slope. Well, we don't exactly use slope here in 3 dimensions. What we use are direction vectors. And those components within the direction vectors are called our direction numbers. In the symmetric format, our direction numbers are in the denominator. This was our A, B, and C. So even though they didn't explicitly come out and say, here is the direction vector, they gave us enough information that if we understand the information that's being given to us, we could easily see what the direction vector is. So we've got our point, we've got our direction vector, and we want the vector format. So I'm going to write this as a vector valued function. R of t is equal to, well, our x component, remember these are going to be linear equations. The direction numbers give us the slope in that particular direction. So for x, it's going to be 5t. And then when t is 0, we're going to pass through this point here. So we would want to have a value of negative 2 when t is 0. So we get 5t minus 2. And then for the y component, we have a direction number or a slope of 2. So we have 2t. And then when t is 0, we want to make sure we're going through a value of 7. So plus 7. And then for the z's, follow the same format, negative 3t plus 3. And that would be the vector format for our line and space.